So our next speaker is Vernon Mowry from Intel. He's a software engineer that works on embedded firmware and BMCs, and he's also one of the maintainers of IPMI and OpenBMC. So he'll be discussing how to improve security and readability at the same time.
So I signed up a couple of years back to be the captain of a sinking ship. It was an intentional thing. I've been working with IPMI since I was with IBM in the early 2000s. So should I stand closer to the mic? Okay. And so I've learned a lot of the troubles that it's had, and so hearing that everybody bag on IPMI, it does make me a little bit happy because I am ready for it to see the end of its life. But I don't want OpenBMC to end up with a steaming demon. Well, IPMI, the IPMID that OpenBMC has, it originated as a proof of concept. So it wasn't really intended to be a long-term solution. But when everybody jumped on this ship, it was the de facto demon. And so I took it upon myself as like, this is something that really needs to change because we've got security issues, and not RMCP problems, but these are people problems. These are coders writing code that is not secure. And part of it is because the APIs that IPMID presented them with to write the code for, the handlers had a hard time. So basically, parsing inputs is hard. And as humans, we tend to make the same mistakes every time. So, you know, you've got to figure out how many bytes you want, what order they're in, and you know, IPMI has a lot of packing of bits into like a bunch of little bits into single bytes, and sometimes they even span across multiple bytes. And then the APIs that historically have been presented are things like void pointers. And if you're lucky, you also get a length to tell you how many bytes you have. So in short, we're just setting ourselves up for failure. And the de facto IPMID that OpenBMC had was not the only one. Every IPMI stack that I've seen up to this point was that same sort of thing where your handler would get a void pointer or a uint8 pointer, and you would take a struct and you would cast the pointer to a struct pointer, and then you would interpret it as if it was a safe thing to touch. And well, computers are great at counting. Humans are pretty bad at it, turns out. I mean, we're pretty good up to 10, 1024 if you use that binary system. But I mean, on the whole, you know, we create the struct and we forget that, oh, there's a reserved byte in there that should be there, or we forget to say it's a packed struct, so the padding isn't quite right because the compiler thinks it knows better than you do, because let's face it does. So there are a lot of issues like that. Also, you know, you've got, depending on what architecture you're on, you've got little or big endian, or you know, if you've got pointers to integers, then that integer might be a different size. Or if you cast a pointer to an integer because you're a bad person, then you also have other problems, like they might not be the same size, so you lose data, or you know, talk to memory that isn't really yours. And sometimes processors, well, I don't know, the ARM processors, they can be told to like be hard about that whole alignment issue. And then you'll get a bus error if you do an unaligned multi-byte access. And then it goes into, or if it's in the emulation mode, then it does a kernel trap. And so you lose a lot of like you're losing your throughput there, and it's just not great. So I found a couple of interesting code snippets from our IPMI stack that some of them are still there, some have been removed and replaced with better code since. But this was part of the motivation. I mean, if you look at this, structs aren't necessarily, well, if you create a struct on the stack, the compiler will do its best to make sure it's aligned and stuff, so that when you mess with it, the multi-byte stuff will all be nice. But in the IPMI handlers, you're not getting something that's on the stack. In the legacy code, it was just a buffer, and then you would get passed a pointer to that buffer. Now, if the buffer was allocated correctly, then it should be aligned. But really, as the handler, you had no guarantees. So taking something like this where you just do a cast and then immediately read a member, that could be a dangerous thing. Also, in this particular case, we have a buffer with no length, so that's fun. We have no guarantees on how long that buffer really was. Another thing is, as you're reading bits and bytes off the stream, you have to know what order that stream was in versus what order your processor is running in. This is something I haven't tried yet, but I know a lot of the ARM chips can bat both ways, right? They can be big or little endian. And by default, we run little endian because I guess that's what Intel chose or something. I don't really understand. But the IPMI spec is mostly little endian. So if you were just writing code and you weren't considering what happened if your BMC was suddenly a RISC processor or something that might be a big endian processor, then the code that you wrote naively wouldn't run because you're pulling off these multi-byte things in your struct and forgetting to do a network to host or that kind of stuff. In addition, bit fields, for whatever reason, swap order as well. So here's a great example of that. This is pretty common in IPMI. Like I said, it was, IPMI started back before a lot of us were born, and when space was important, and so they would pack as many bits into the smallest space as they could, which gives you bit fields, and then you end up with code like this if you're unlucky. So here they actually did do a request or length check, but they still did that great static cast. And because it's a bit field, there should also be the if big endian, else if little endian, so that you can switch those bits around. And that, I mean, in addition to just looking great in your code, half the time it gets coded up wrong anyway, because we forget which order the bits go on endian order. So this is just, another example of the many ways that we can go wrong in code. So is the code sanitary? If you have to ask that question, it's probably not. So here's a bunch of things we can look out for, but ultimately we're going to miss one probably. So it's better to just come up with a framework that just doesn't have these, right? If you're not ever passing around a pointer to a buffer, you don't ever have to worry about that buffer getting overflowed, right? So I'm not saying that pointers are necessarily bad, but they definitely invite abuse. So one last poor code exhibit. So void pointers don't offer size, just an address. And this in-out pointer is just asking for trouble. So the data length pointer, you get it as a length of how many bytes you received in buffer, but it also, you're supposed to write how many bytes you're returning in the other buffer. And this is part of the legacy API for IPMID. So every function has the same sort of look and feel. So good security is up to the user who's coding it up, but when you're writing the API, you can write APIs that discourage these poor practices. So I'm not sure if we even really need this slide at this point. It's pretty obvious that the code was meant for an overhaul. So the goals for this, I really wanted to come up with a way that made the compiler do the heavy lifting. Like I said, people tend to make the same mistakes. You look at a function and say, okay, yeah, this is the sort of thing I want to do. Copy, paste, modify, compile. Oh yeah, it works. Forgetting that every error you had in the original code is now in your code as well. And when that one gets fixed, yours might not. So leveraging the compiler, which is more likely to be writing good code than you, is important. I wanted to focus on the parsing of the packets, because having these packed structs and stuff was just a mess. We would end up with all sorts of weird padding errors and the pointers. Oh, the pointers. So I thought, okay, I looked at SD-Bus Plus, and they were doing a lot of this packing, unpacking based on the type of the tuple that it had. And I thought, okay, we should be able to do this with IPMID as well. I did realize as I was implementing it, there were some differences. When SD-Bus Plus was doing it, they have a message that has encoded in the message the data types, so that they could take that, unpack it to those data types, look at the function, see what data types it was looking for, and try and match them up and throw some error if it didn't match. With IPMI, unfortunately, the data is not encoded into the message. So I did have to rely on the function arguments to do some sort of data checking. And really the best we can do at that point is make sure that the sizes match up. So the APIs hopefully would be easy to use. I think that when you're writing a library or an interface like this, it's important to make it easy to use correctly and hard to abuse. And that sometimes means that the internals of the library are complex, but it should be pretty straightforward to use. IPMI does have some functions that are variable length. Most of them are fixed length, but it did need to have a way to handle variable lengths, especially ones where you know it's a fixed length here, but then the payload beyond that depends on the contents of those fixed bytes. So like a subcommand sort of thing or something like that. So we needed to be able to handle that as kind of a special case, but still make it safe to do that, right? I still didn't want to say, oh, you get a byte and then a vector. That's a possibility, but hopefully that's not the way that it's being used. Yeah, okay, that does cover the slide. In addition to the variable packet length, sometimes you've got these bit fields, and that needed to be handled as well. There aren't really any good bit types native to C. C++ does offer some of those, but we weren't really using any in the old API. So rather than, I mean, if we were doing just the C style stuff, then we would definitely want to shift and mask. But I don't want to tell the user to do that because they probably won't. So this is basically what the IPMI spec looks like. It's kind of a mess. You've got, you know, bits and bytes that are mixed up, and you've got, you know, reserved bytes scattered throughout it. And, you know, this one in particular has a variable payload, and it needed to be able to handle this, right? This actually wasn't even the worst one. I think William ran into the worst one when he was trying to do the land set parameter command. So this is basically what I came up with after talking with several people, including the other IPMI maintainers. We came up with the idea of, you know, you specify each parameter as a separate thing, right? You say, okay, well, the first parameter I need is a 7-bit integer, so or a Boolean, a 1-bit integer, and these variable things that you asked for them individually, and then when you registered this handler, the registration process would say, okay, let me inspect this function. It needs these types, and then it, you know, it would extract it would know how to extract those from the payload when the message was called. So this did involve creating some new data types. You'll notice uint4 and uint3. Those are not standard C types. So I did some leveraging of the Boost multi-precision library, where it lets you define arbitrary precision integers. And they, for the most part, they act just like regular integers. They just take up a little bit more computation. But it allows you to think in this space where you're asking for a specific thing, and that's what the parser will give you. Yeah. So that was what the first slide was, kind of what a new function would look like when you're registering it. And this is what the what happens when the message is coming in to be executed. This function, it takes a request, which is basically metadata plus the data that was pulled off dbus. So it does get a big buffer. In this case, it's a standard vector, which has encoded in it a length as well as the pointer. But the request then takes the callback, which is part of this class, and it uses the Boost callable traits, which allows it to, at compile time, it's doing this. It extracts the parameters of the function as a tuple, and then using variadic templates, we're able to extract those tuple members one at a time as part of this. So the unpack call, it looks so simple there. We say request unpack, where the thing that you're unpacking is actually a tuple of the parameter types for the function. And that gets expanded kind of recursively by parameter templates into compiled functions that extract each one at a time. And then after it attempts to extract it, it says, well, the extraction can fail at any point in time, right? So if you tell it, I want you to extract a 4-member array of byte, uint 16 pairs, then if it has too many bytes or too few bytes, by the time it gets to the end of that array, then it'll throw an error. And then it'll respond with the appropriate, insufficient bytes or wrong number of bytes message. If it happens to unpack successfully, then it has this tuple, and then standard apply will basically call a functor with a set of parameters, so that from the function's perspective, it was just called as if it had those parameters passed in. So this is a pretty simplified view. There are multiple cases because I did want to make it a lot easier to use, but this is the basic overview of how it happens, right? The function gets passed in a bunch of stuff, and then it passes back this kind of thing called a response, which I think I forgot to talk about. Oops. Let me go back. So I did forget to talk about what a response is. So when you define a function handler, being able to return something kind of the same way that you receive it, you get to choose the shape of the thing that you're returning with this our response type declaration, where you basically pass in the types of a tuple that you want to return, and then you return a tuple that will then get packed back into a bit stream that can get sent back to the caller. So in this case, it's returning a vector of bytes, which isn't very interesting. But here, the handler returns that tuple, and then it packs in the return code and then sends it on its way. So this is where the magic kind of happens. We've got a couple of unpack things where when you call unpack, this is what is getting called under the covers. So for each type, there's an overload to this template that gets called by the compiler, so that each type has a specific set of code that knows how to unpack that type properly. And this includes multi-byte integers and arrays and vectors and tuples and all of the various types that this API can handle. It knows how to properly unpack each one of those. And some of this means that it's kind of doing a recursive thing. Like if you unpack a tuple, you actually want to unpack all the members of the tuple. And if that fails, then the tuple failed to unpack and you return the response there. So some of these unpack functions are a little more complex than others. Whereas, like if you decided to unpack a single byte, it's just to, advance the count in the payload and pop the next byte. But it did offer a way to keep track of. You can unpack a single byte, a single bit, or various things, and then in case of if you're trying to unpack a byte when you haven't cleared out the remaining extra bits, that can throw an error as well. So these alignment issues and stuff can be caught as well. So this is all part of pushing the complexity into the library internals. So in addition to just being able to request the various basic types, I wanted to be able to pass in some of the metadata as well. So that's what this IPMI context thing is. It passes in information like the channel that it came in on, and it passes in a yield context, which allows the handler to be executed in an asynchronous yielding API so that we don't end up with high latency handlers. And it passes in a payload, or you can request a payload, which allows you to manually make these unpack calls in like the case of the setLand parameter, where the first byte tells you what parameter you want, and that's how you know what types to unpack. In this case, you could you could request a payload, and then using that payload object, you could say, okay, now I need these 12 types or whatever. So these extra metadata options are available for advanced functions that need to do special things. Initially, when I first started writing these, I think the first handler took me about 15 minutes to rewrite. And after that, it was pretty easy. And I got quite a bit of feedback from people who were actively rewriting the handlers, and it was, for the most part, positive. There were a few patches that needed to come in to handle corner cases that I hadn't come up with. But for the most part, it was exactly what we wanted. It was easy to use, and it provided a very safe mechanism for parsing these inputs and creating the outputs. So we created this new API, but all of the code was still in using the legacy handlers. So in the meantime, I did create basically a shim handler that would just unpack the entire thing as a vector and send that out to the handler as a void pointer, unfortunately. But it means that all the old code would still work while we're trying to rewrite it. And because I wrote it as a separate mechanism that way, once we clear the bar of rewriting all the handlers, then we can just easily pull that code out and only support this new API. And we are making slow progress, but it is progress indeed. And even some of them are actually using the async mechanism as well. And I still have some patches that I'm working on to make it even easier to use some of those async things. So it, like I was saying, it did create the environment that I was looking for. You no longer have to rely on people to write code that is counting every byte, because that part's already done. That part, not only was it done, but I also wrote my first unit tests. Yay. And the unit tests tested the packing and unpacking of the payload, because that was the critical portion that I was trying to fix. I wanted to make sure that that part was correct. So I did write a bunch of tests, unit tests that get executed when you're building. But now that means when this is all done, we can get rid of C-style casts and void pointers and buffers, and hopefully eventually this will also lead to a new era of unit testing, where we can have interfaces well defined and have small testable functions, so that by the time IPMI dies, we will have something that is way more beautiful than it currently is. And I apparently talked way faster than I was supposed to, or something. I don't know. Are there any questions? I think that's the end of my discussion here.
So, with so many inputs you accept in different types, won't it put a load onto the stack?
There is a little bit more code generated, but it's all correct. So it was the code size of IPMID did increase.
Yeah, I saw that.
Everybody saw it. But I am of the opinion that it was worth it, right? Processors are only getting more powerful.
So not only that, not only the size of IPMID, because if we guys are doing the OEM IPMI library also, size of that library also increased nicely. Like it adds
Right,
extra bytes to the whole image.
right.
If you don't like it, don't use IPMI anymore.
Yeah, that is another option from a co-maintainer. See, we're all rooting for the same thing. Redfish is a great alternative.
But Redfish is not lighter than IPMI.
It's not, but it is at least over a safe transport. I mean, any security and coding mechanism that does this is going to add some overhead. And yes, if you hand coded perfectly every one of your handlers, you would probably end up with less code, a smaller compiled code. You would also be, you might win a Nobel Peace Prize.
So, if I understand this correctly, does this mean that we are moving the specification of the requests and responses from packed structs into function parameters?
Yes. So the idea is the function parameter looks a lot like the API specification, where you have 7 fields in and 2 fields out, and that's what your function does.
Do you have any place where there's an example of how we would potentially handle cases where the first byte says I am this message, and then it essentially describes how we are going to interpret the remaining parts of the bytes? Like I mentioned optionals as the...
Yeah, there's a code review. It hasn't been merged yet. But William had a code review for the setLand parameter, which, like I said, is the first byte tells the size or the type of the message. And then in a giant switch statement, it says, okay, we need these types, unpack it here. We need these types, unpack it here. And really what happens is you're using that same payload object and you're just calling unpack with the 5 types that you need instead of just receiving them as function parameters. You instantiate those 5 things on the stack and then call unpack referencing them.
So not only in case of OEM commands, the first byte is not always the length, like they are down the line. So how will the pattern goes? Like where it will...
Well, it depends on if you're doing OEM commands the way the IPMI spec does it or the cheater pants way. So if you cheat and you just define your own OEM number, then it's the same way as any other IPMI thing where there aren't any extra bytes. If you do it according to the spec, there are group OEM commands and just OEM commands. And those, when you register them, you tell it, register it with this group or with this code, and then those get handled magically for you.
Okay, you mentioned that the old API does not work, only work on little ending systems, but not on big ending systems. How about the new API? Does it resolve the byte order issue?
This should resolve the byte issues. I haven't tested the old API. It might work okay on big endian systems, but I haven't tried it. So, but when this code is unpacking a multi-byte integer, it does the right thing and uses shifting and ORing instead of just casting. And because shift and OR, they do the right thing based on the endianness of your system, then it always works.
it also works for packing, right? Because unpacking is
Yes.
passing the request. You need to also pack the response. So it also works for packing
Right.
on beginning systems.
Yeah. So packing and unpacking, I did have to create pack and unpack methods for each type, but they basically do the inverse of each other. So when you're packing something, you're shifting and masking.
Okay, thank you.
With IPMI payload type, you still expect us to typecast those?
The IPMI payload.
The
Type?
type you explained that there are two types, right? The context and the payload.
Oh,
So if you take as a payload,
oh, if you get a payload, it's an object and you perform regular operations on it. So you don't have to cast things. You can call pack, well, if it's a request payload, then you're calling unpack on it, and it does all of the checking and stuff the same as if it got passed into the function.
Yeah, I was wondering, the library you use for new API, the parsing code, the pattern unpack, is that available for perhaps other daemons as well?
It's funny you would ask.
Because I do see, like, for PODM, for example, we have this very similar problem. We are
Right.
packing bit fields, or the response can be variable length.
Right.
It's almost the same as IPMI.
I did not pay him, I swear, but this is exactly one of the questions that I did want to happen. This is not an IPMI specific thing. Like I mentioned earlier, the ideas I stole from SD-Bus Plus. And so the notion of being able to inspect a function and pack and unpack based on some tuple is generic. In the dbus case, we also had extra metadata in the message type itself, but I assume PLDM is just packing bits, kind of like IPMI does.
Yeah, it's very, very similar. And also,
So-
like, the response type can vary based on, let's say, first byte will tell you, how many more bytes to expect, for example.
Right. So the library itself, well, the library, it's all just headers in the IPMI code base, but there probably are enough tie-ins to other IPMI stuff that you wouldn't want to just use it directly, but you could certainly cut and paste and stuff. But the ideas exist across many domains. That's why in the title of the presentation, there was nothing about IPMI itself. It was improving security and readability at the same time. So yes, this could help PLDM. Keep in mind, it will increase the binary size though.
Right. Thank you very much.
You have the similar thing in BMC web also, where
Not currently, but I think Ed was considering something like this. Ed was very jealous that I did this to IPMI and he didn't get to do it first. So if you goaded Ed enough, maybe he would do it for BMC Web as well.
I think it is there, right? JSON which we are passing.
For JSON.
Yeah.
Okay. What he didn't do, so the parsing is there, but and that's equivalent to the SD-Bus Plus, but the SD-Bus Plus ASIO mechanism, you get to specify the parameters to unpack that way instead of calling unpack. So that's the only difference. It was messing with the function callable traits and that kind of stuff that makes this differ from the BMC web stuff.
Yeah, two good points that you can carry back to Ed. One is definite applause for your use of unit testing. Another is the way that you implemented for IPMID using variadic templates is actually superior to what was done for SD-Bus Plus. The issue there is that if you're using variants and templates, you have the ability to generate a runaway template case within the compiler. So for example, I have a couple cases I'm dealing with now where I add in SD Bus Plus, create one of its structures for a response, and my code goes from 200K to 9 megabytes.
All right. Any other questions? All right.
Any more plans to add more functionality to IPMID? Like, as less of point supported,
Well,
or as making it more generic to be used?
I'm not sure that I have any specific plans of adding more commands because, well, we're expending more effort on improving Redfish and that kind of stuff because we do want to encourage people to move away from IPMID. But there are some other improvements to IPMID that I would like to see.
Thanks for the talk. This is a comment on moving away from IPMI. I commend it. But we're stuck with it for the host to BMC interface for probably a very long time. So as much as Redfish will get rid of the kind of network-facing aspects, we're stuck with IPMID for a long time.
All right. I think that's all then.